While the math interest group started out on topics related to early Greek mathematics, it progressed to topics at the high school and college level, and more recently covered the very boundaries of mathematics in science. What is knowable, provable, computable? Topics like Cantor's different types of infinities, Gödel's incompleteness theorem, where some theorems can neither be proven true nor proven false, Collett's conjecture and Riemann hypothesis, whose proof or counterexamples still remain elusive, and Wolfram's way to model physics with automata and hypergraphs. There was no grand design in deciding on these topics, but they actually do dovetail into today's talk, in which an article written for the Bell Labs Journal in 1962 by an obscure person who even people working in Mary Hill may not know, but promises some hope for unprovable mathematics. Our speaker for today for the math interest group is Al Aho, and he's giving a talk on computation and the Busy Beaver function. Just to recap what I mentioned in a previous talk that he gave, Al earned his degrees at the University of Toronto, and it's got a PhD at Princeton. And at Princeton, he became friends with Jeff Ullman, a fellow PhD candidate, and he would later meet up with him at AT&T's Bell Laboratories in Murray Hill. Their collaboration, which started in 1967, along with some authors, resulted in several books. These are books on design and analysis of computer algorithms and the so-called Dragon series of compiler design. These books have become a staple of computer science degrees for several generations of students, myself included, as I have benefited from taking the computer science graduate courses that were taught from these books. Al helped Stevens Institute in setting up their computer science program and later taught computer science at Columbia University, receiving a Distinguished Faculty Teaching Award in 2014. He's received other awards too numerous to mention, but the latest is the AM Turing Award in 2020, which he shares with his colleague and friend, Jeffrey Ullman. He's given talks for MIG before. In 2019, a talk on complex linear algebra, underpinnings of quantum computing. In 2020, P versus NP, which is a Clay Prize problem. And Alonzo Church's the V-lambda calculus, a software equivalent of the Turing machine. In 2021, the evolution of programming languages. And without further ado, Al Aho on the computation of the Busy Beaver function. If you could screen share.
I was motivated to give this talk because of the last talks that Walt gave on the Collat's problem and the the Riemann hypothesis. Before I begin, how many of you have heard why computer scientists get confused between Halloween and Christmas? And the answer is because when they see the dates OCT 31 and DEC 25, they think they are equal because the octal representation of 31 is decimal 25. Okay, let's get on to something more serious. What I'd really like to talk about today is what problems can computation effectively solve and not solve? I'll set the stage for this question by defining the three key words in this question: problem, computation, and solve. Now, as we all know, there are infinitely many different kinds of problems in real life, but for the purposes of this talk, I'm going to only talk about two kinds of mathematical problems: decision problems and the problem of computing the value of a function at a given point. A decision problem is a question that has an answer which is either true or false, or we hope that it has an answer that is true or false. Two of the most famous decision problems in mathematics are the Riemann hypothesis, which Walt talked about last time, and Goldbach's conjecture. Is every even integer greater than 2 the sum of two prime numbers? And I'll talk about this in a little more detail shortly. And the problem of computing the value of a function at a given point is we're given the specification of a function and we're asked to determine the value of that function at a given point, a given value of its argument. By computation, I am going to use the gold standard model of computation in computer science, namely the Turing machine, and I'll explain in a little more detail how a Turing machine works shortly. A Turing machine, I might point out, is a very primitive computing device, but the remarkable fact about a Turing machine is that it can compute any function that the most powerful supercomputer in the world can compute. The Church-Turing thesis states that any function that can be calculated by an effective method can be calculated by a Turing machine. Now, just a little more terminology. Let us define the word string as a finite sequence of symbols drawn from some alphabet, and the word language as a set of strings. This is a very broad definition because under this definition, English is a language, Python is a language. It's a set of integers that are prime numbers forms a language. And what we will mean by the membership problem for a language is to determine whether a given string is a member of that language. So we could, for example, ask, is the string 323 in the set of prime numbers? We can classify languages by the difficulty of solving their membership problem. And this is the sort of diagram you see in the first course on theoretical computer science. The outer oval represents the set of all languages over some alphabet. And a language is a subset of the set of all strings over that alphabet. And as Thad in his talk on Cantor infinities showed, this means that there are an uncountably infinite number of possible languages, since there are an uncountably infinite number of subsets of the countably infinite set of all strings. The middle oval represents the set of all languages that can be recognized by a Turing machine. That is to say, each element in the second oval is a language such that there is a Turing machine that will recognize every string in that language, but may not halt on a given string not in the language. Using the terminology of mathematics and formal language theory, we call such languages recursively enumerable languages. The inner oval represents the set of all languages that can be recognized by a Turing machine that halts on all inputs. We call such languages recursive languages. This classification scheme for languages forms a proper hierarchy. We can prove that there exist languages for which the membership problem is so difficult that the language cannot be recognized by any Turing machine. That is to say, given one of these languages, there is no Turing machine that can determine whether a given string is in that language. We call such languages non-recursively enumerable languages. Then there are some languages whose membership problem can be partially solved by a Turing machine in the sense that given a specification of a language and an input string, we can construct a Turing machine that will always halt and answer yes if the string is in the language, but there may be some strings not in the language for which the Turing machine will not halt. Finally, there are some languages whose membership problem can be totally solved by a Turing machine in the sense that given a specification of a language and any input string, we can always construct a Turing machine that will always halt and answer yes if that string is in the language, and answer no if the string is not in the language. These are the recursive languages. A Turing machine that halts on all inputs is a definition of an algorithm. Thus, a language is recursive if and only if its membership problem can be solved by an algorithm. And we can prove that there are recursively innumerable languages that are not recursive. Now let us consider the problem of evaluating the value of a function at a given point. We will say a function is computable if it can be evaluated by an algorithm on a Turing machine that halts on all inputs. If it cannot be evaluated by such a Turing machine, we say the function is uncomputable. The essence of this talk is to present the Busy Beaver function, which is a well-specified example, and now quite a famous example of an uncomputable function that generates notoriously rapidly growing sequences of numbers. As a way of introducing rapidly growing sequences of numbers, let us consider Ackermann's function. Wilhelm Ackermann was a student of the great mathematician David Hilbert. In fact, it was Hilbert and Ackermann who in 1928 introduced into mathematics the term Entscheidungsproblem, which means decision problem in German. Alan Turing's famous 1936 paper was titled On Computable Numbers with an Application to the Entscheidungsproblem. The definition of Ackermann's function is shown in blue on this slide. The slide also has a detailed evaluation of Ackermann of 1 and 2 shown in green. Note that the first step of the evaluation uses the third equation to create an additional level of recursion, as does the second step. Ackermann's function is famous for its rapid growth. It produces a hierarchy of growth operators. The first operator in the hierarchy is addition. The next is multiplication, then exponentiation, then an operation called tetration, which is iterated exponentiation, and so on. You can see a picture of tetration as a stack of exponentials, as shown on this slide in the evaluation of Ackermann of 4 and 4. Note that Ackermann of just 4 and 2 evaluates to a huge number. It has 19,729 decimal digits. The Ackermann function is also notorious for the huge number of recursive function calls it makes. In many programming languages, trying to compute A of 4 and 2 produces a segmentation fault. I tried awk on A of 4 and 2, and sure enough, it produced a segmentation fault. And I invited some other people, including Griff, to see if he could evaluate A and 4 and 2 in his favorite programming language. And he reported segmentation fault as well. Here is a quote I found in Wolfram's Math World webpage. It said, the Ackermann function is the simplest example of a well-defined total function which is computable but not primitive recursive, providing a counterexample to the belief in the early 1900s that every computable function was also primitive recursive. The primitive recursive functions model computer programs with bounded for loops. I'd now like to turn to an even faster growing function called the Busy Beaver function that was introduced by the Hungarian mathematician Tibor Radó in a paper titled On Non-Computable Functions, which appeared in the Bell System Technical Journal in 1962. A very unusual place for a paper on non-computable functions. Radó was a remarkably diverse mathematician who did work in topology, analysis, and the mathematics of computation. He was born in Budapest in 1895. He was a first lieutenant in the Hungarian military, and during World War I, he was a prisoner of war in Siberia. He escaped and walked over 1,000 miles before arriving back to his home in Budapest in 1920. He moved to the United States and, amongst other tasks, helped found the mathematics program at Ohio State University, and he consulted for the United States government during World War II. He died in Florida in 1965. Radó's function was defined by playing a computational game he called the Busy Beaver game. I don't think he chose the reason Busy Beaver because beavers are notoriously good in math. They love logarithms. I think he chose the name because he had the idea of a Busy Beaver computing the function on a Turing machine and the Busy Beaver moving back and forth across the input-output tape. As we shall see, if we can determine the value of the Busy Beaver function for certain input values, we can solve some of the most famous decision problems in mathematics, like Goldbach's conjecture and the Riemann hypothesis, which Walt talked about. Radó's game consisted of finding simplified halting Turing machines he called Busy Beavers and determining the maximum number of moves any such function could make. The specification of a Busy Beaver machine is both simple and precise. A Busy Beaver machine is a Turing machine with end states plus a halt state which has no moves. The machine uses only 0 and 1 or 1 in each of the cells of its input-output tape, and its move function is stored in the finite state machine. The move function maps a state and a tape symbol into a triple consisting of a tape symbol, a move direction, and a machine state. Here is an example of a Busy Beaver machine with two states, A and B, plus a halt state H that has no moves. The move function is just a table whose rows are labeled by the states and whose columns are labeled by the tape symbols 0 and 1. The entry 1R, comma B for move A and 0 means that when the machine is in state A, looking at the tape symbol 0, it will rewrite the 0 to a 1, move the tape head one cell to the right, and then enter state B. Initially, the input-output tape contains all zeros, and the tape head is over some cell of the input-output tape as shown in the figure on the right. We will use BB of n to denote the maximum number of moves that any end-state Busy Beaver machine can make, starting with an input-output tape of all zeros, and then eventually halting. The purpose of Radó's paper was to present a function that was easy to specify, but undecidable to compute. And BB of n is one such function. A Busy Beaver machine that makes the maximum number of moves among all halting machines of its side is said to be a champion Busy Beaver. Essentially, Busy Beaver of n is the longest running time of a halting Busy Beaver machine with end states. Radó's game, or what he suggested, was that contestants could play the game by finding Busy Beaver machines that are champions. To illustrate how a Busy Beaver machine works, let us go through the sequence of moves that the Busy Beaver machine I showed on the previous slide makes on an input tape initially containing only zeros. So this slide shows the first move which the machine makes starting off in a tape containing all zeros. The machine is in state A, the start state, and at the beginning of the move, the machine consults the move function for A and 0, and it sees the entry 1R comma B, which means that the machine rewrites the 0 under the tape head into a 1, then moves the tape head right 1 square and enters state B, as shown in the second line in the diagram on the right. Here is the second move. The machine is looking at a tape cell 0. It's in state B. It consults the move function and sees that the move for state B and 0 is 1L comma A, which means that the 0, it rewrites the 0 as a 1 and moves the tape head 1 cell to the left and enters state A, as shown in the last line on the diagram on the right. So continuing in this fashion, here's move 3, 4, 5, and 6. At the end of move 6, the machine has written 4 1s on the input tape and has entered the halt state from which there are no moves. So it's very easy to trace out the sequence of moves that a Busy Beaver machine makes. What is fiendishly difficult is proving that a given Busy Beaver machine is a champion Busy Beaver, showing that there is no Busy Beaver machine with the same number of states that makes more moves than that champion machine. And what's interesting also about this is that when I first joined Bell Labs, I met Shen Lin. And Shen Lin is famous as being the co-author with Brian Kernighan for the Lin-Kernighan heuristic for solving the traveling salesman problem, and the Kernighan-Lin heuristic for solving the graph partitioning problem. And Shen Lin was a student of Tibor Radó's. I haven't met anyone who I knew at Bell Labs who had met Tibor Radó, but I wish I had known about this paper that Tibor Radó had written, and also the paper that Shen Lin and Tibor Radó published in the Journal of the ACM, where they showed that the Busy Beaver function for 3 has the value 21. And this result is included in Shen Lin's PhD thesis, and it's a tour de force of computer simulation and ingenuity in coming up with the answer that there is no Busy Beaver machine of 3 states that makes more than 21 moves. In the past 60 years, some lower bounds and values for the Busy Beaver function have been computed for only a few values of n. And what you'll notice is that even going to Busy Beaver of 5 and 6, we're getting astronomically big numbers. I'd now like to mention a few results from a paper that Scott Aaronson wrote back in 2020. Scott Aaronson is a brilliant theoretical computer scientist with deep interests and results in computational complexity theory and quantum computing. He is author of the Complexity Zoo, which diagrams the known relationships amongst 400 known computational complexity classes. And he's been in the news relatively recently for devising the problem that's supposed to demonstrate quantum supremacy on quantum computers. But I'd like to just focus on some of the results that he mentions in the paper that he published in ACM SIGAC News in 2020, titled The Busy Beaver Frontier. The first observation is that the Busy Beaver function grows faster than Ackermann's function, that BB of 2n is greater than or equal to the Ackermann function on the arguments n minus 2, n minus 2. It is relatively easy to show that the Busy Beaver function grows faster than any computable function. And this was Radó's intent in publishing his paper to begin with, to show a simple function, easy to specify function that grows faster than any computable function. So it's not computable. Now, one of the interesting results mentioned in Scott Aaronson's paper is that if you can compute a certain value of the Busy Beaver function, you could prove Goldbach's conjecture. And just to remind you, Goldbach's conjecture states that every even integer greater than 2 is the sum of 2 prime numbers. This statement has been verified up to something like 4 times 10 to the 18th power. But what's interesting about this conjecture is that it was proposed by Christian Goldbach in 1742 in a letter to the great mathematician Leonhard Euler. And this 280-year-old conjecture of Goldbach remains open even to this day. You could achieve immortality in the mathematics world by proving this conjecture one way or the other. But if you know about the Busy Beaver function, here's one way to approach this function, which is somewhat unusual. In 2015, a GitHub user published a 27-state Turing machine that halts if and only if Goldbach's conjecture is true. This 27-state Turing machines works by systematically counting up through all even integers greater than 4. For each even integer I, it tries all possible ways to create I by summing 2 smaller integers greater than 1, and then checking if the 2 integers yielding the sum are both primes. And if it finds such a pair of primes, it moves up to the next even integer and repeats this process. If it finds an even integer that cannot be produced by summing a pair of primes, it halts and it declares the Goldbach conjecture is false. So this Turing machine could be used to prove the Goldbach conjecture if we knew the value of Busy Beaver of 27. And the reason for this is that Busy Beaver of 27 provides a bound on the maximum number of moves any 27-state Turing machine can make. So one way of solving the Goldbach conjecture is to run this Turing machine, and if the Turing machine made more than Busy Beaver of 27 moves, we know that it would never halt. So this would then prove that the Goldbach conjecture is true. On the other hand, if it halted before it had made Busy Beaver of 27 moves, it would have printed the Goldbach conjecture as false. So this looks good, doesn't it? But here's the rub. This is not a practical way to solve the Goldbach conjecture, because Busy Beaver of 27 is such a huge number that it is not physically possible in our universe to simulate a Turing machine through that many moves. Another interesting fact that Aronson mentions in his Busy Beaver Frontier paper is that in 2016, he and two colleagues created a 744-state Turing machine that halts if and only if the Riemann hypothesis is false. And it uses a similar kind of argument of looking at all possible zeros of the Riemann zeta function and seeing if they lie on the line 1/2, or the real parts do, as Walt mentioned in his talk. And if we knew the value of Busy Beaver of 744, we could solve the Riemann hypothesis in the same fashion that the Goldbach Turing machine solves it. But again, this is even more preposterous because Busy Beaver of 744 is just a mind-blowing sized number. I could keep mentioning many other interesting facts from Scott Aronson's Busy Beaver Frontier paper. One of the more intriguing facts he mentions is that using the Busy Beaver function, we can show that there are problems in mathematics that cannot be solved with using Zermelo-Fraenkel set theory with the axiom of choice. So this paper starts exploring some of the roots of what's provable and not provable in mathematics. And what I'd like to mention is that recently, John Pavlis wrote a very easy to read paper in Quantum magazine titled "How the Slowest Computer Programs Illuminate Math's Fundamental Limits." And in it, he says, the goal of the Busy Beaver game is to find the longest running terminating computer program of a given size. And its pursuit has led to surprising connections and to some of the most profound questions and concepts in mathematics. In fact, there's a web page on the internet devoted to the most recent results on attempts to get precise values or bounds on the Busy Beaver function. And if you're really interested in it, I encourage you to look at this web page. But to finish up, I will leave you with what I and many other computer scientists find as one of the most intriguing open questions concerning computation. We've seen the classes of problems that computation can and cannot effectively solve. But the underlying question is, are there more powerful ways other than computation to solve problems effectively? And with this question, I will stop the talk and leave it open for discussion and questions. So, any questions?
All right, good. Yeah, great talk. It was very interesting. But I'm wondering about this computation issue that, some are not solvable and you don't reach an answer. Now, is it because the machine is going through infinity and the answer is someplace out there and we can never approach it? And therefore, because we can't approach it, it's not solvable. So could there be an answer that's true? It's just out of reach.
Well, as Radó, or by the way, I looked up how to pronounce R-A-D-O on the internet, and I got 3 different pronunciations. There was a Brit who said it's pronounced Radó, and then there was a Italian who said Radó, and then it must have been an American who said Radó. There is a radio company, apparently. So if there are any Hungarians in the audience, and Hungarian and Finnish are cognate languages. So in Finnish, one would say Radó. But I would be curious as to what the correct pronunciation of his name is. But an intriguing aspect of why I'm giving this talk and what interests me about this is, why can we define problems, say in computer science and mathematics, that we can prove have no algorithmic solutions? And even if we look at Turing machines that do not halt on inputs that are not in the language, but are in the language, namely recursively enumerable languages that are not recursive, we can prove using a diagonalization technique similar to what Cantor used to show that there are, in the space of all languages, languages that can't be recognized by any Turing machine, one that doesn't even halt. So I think it gets into perhaps the nature of infinity, which you talked about. And I wish I had actually heard your talk, because there's a lot of speculation of, does infinity actually exist in the physical universe? I might mention there's a great movie on Netflix called A Journey to Infinity. And many mathematicians and scientists say that infinity does not exist in the physical universe. It does mention the Infinity Hotel, which I think you spoke about as the Hilbert Hotel or the Hilbert's Grand Hotel. But there was some speculation by some of the physicists as to whether infinity exists inside a black hole in the curvature of the singularity inside a black hole, which curves space infinitely. But that's yet to be proven, and that's way beyond my pay grade. But you raise, I think, a very profound question of what is knowable, and there's reason to believe that there are facts that are true that we will never be able to prove. So the knowability frontier is a wide open question. I once thought that praying to God is a more powerful way of solving problems than using a Turing machine. But on the other hand, I don't think praying to God is effectively computable in that sense that you can solve all problems just by praying to God. You can solve a lot of problems by praying to God, but I'll leave that to the theologians and the philosophers.
And I have one more question, if I can.
Yes.
Oh, okay. You look at the languages, they're made out of symbols, and there's a finite symbols that you might use, but those symbols can make that an infinite number of possible sentences. But we can translate all of those into Gödel's numbers. And is some of those Gödel's numbers, they're all going to be prime. And that lets you get back. Is it the transcendental numbers that are out there, the numbers that we can't grab hold of very well? And because of that, we can't get completeness everywhere.
It's an intriguing thought as to what gives rise to non-computability. I guess the great David Hilbert thought that every theorem in mathematics had to have a proof of the correctness of that theorem. And then Alonzo Church and Alan Turing came along showing that there are problems, computable problems that you can specify that have no algorithmic solutions. So they were not effectively computable, either in the lambda calculus or on a Turing machine. And I guess Gödel's incompleteness theorems show that if you have a sound and complete axiomatization, in that axiomatization, there will be true statements that cannot be proven. So I view this as maybe lifelong employment for mathematicians, that no matter how you axiomatize mathematics, there will always be true statements that you can't prove, but you could incorporate into your axiomatization and then come up with a new axiomatization then that admits of more true statements that are not provable. And my real interest in all of this has stemmed from my background in programming languages and their compilers, where you need a way to specify a computation to a computer. And the best ways that we know of to date involve encoding the program in some kind of programming language. And the programming language uses a discrete alphabet, what you can type into a computer. Maybe people are experimenting with spoken languages, but the spoken languages are encoded using some kind of analog to digital encoding, so then they can be executed on a computer. And the computers that we have today use binary logic ultimately. Even quantum computers can't do anything more than a Turing machine can from a theoretical perspective.
Okay.
All right, thanks a lot, Al.
Jim Landwehr, you're next. Would you please unmute yourself?
Yeah, that's interesting now. Maybe my question was going to be about quantum computing and how that might relate to any of all this, which you just sort of touched on in your last sentence. And I wondered if quantum computing, so that sort of came up after all of this mathematical and these formalizations were set up. And I'm wondering if quantum computing changes anything theoretically about what is and isn't computable and so on in the topics you've talked about. And second, whether it changes anything practically about what, if you could actually do quantum computing on some sort of a reasonable scale, does it change anything practically about computing any of these functions that you've been talking about?
That's a great question, Jim. From a theoretical point of view, Turing machines can simulate quantum computers. So the class of functions that you can compute on a quantum computer is no greater than what you can compute on a Turing machine. However, there is the physical Church-Turing thesis that says that anything that you can compute on a quantum computer, you can compute efficiently on a Turing machine. And efficiently means within the same polynomial time bound. And the holy grail of quantum computing, practical quantum computing, is to find a problem that you can solve faster on a quantum computer than you can on any digital computer.
So I thought this cryptography topics produced such things, these factoring huge numbers that goes into the security systems that we use, and that could be broken by, at least as I understood it, theoretically broken by quantum computers.
Well, what is known is that Shor's algorithm allows you to factor integers on a quantum computer in polynomial time. And there is no known classical algorithm on a digital computer that can factor polynomials in polynomial time. But it's not proven that you can't do this. So you can make yourself immortal again in mathematics by showing that there is a polynomial time factoring algorithm for a digital computer. But what Scott Aaronson proposed, and what the great interest in quantum computing is, that are there functions that can be computed on a quantum computer faster than on any digital computer? And some of this work on boson sampling was aimed at this direction, but the jury is still out. Nobody has been able to find a function that a quantum computer can solve, even theoretically, that's provably faster than what you can do on a classical computer. But if you could show, for example, that Shor's algorithm could be implemented in polynomial time on a classical computer, you would have exhibited quantum supremacy from this point of view, that here's a function that a quantum computer can solve in polynomial time that a classical computer cannot. So the NIST took this so seriously that it issued a new initiative to find an encoding scheme that cannot be solved efficiently on a quantum computer. So there's some interesting work on lattice space codes, but it's still unproven as to rigorously as to whether they can be done in polynomial time on a classical computer. But on the other hand, nobody has exhibited an algorithm on a quantum computer that can solve these lattice space codes in polynomial time. So it's a very intriguing area of mathematics at this point. But as this Busy Beaver function indicates, we're now dealing with some very, very difficult problems in number theory. And number theory is something that just amazes me. You have to spend about 6 or 7 years getting to the frontiers of the field to be able to prove a theorem that maybe 3 or 4 people in the world will understand. So it's not for the faint of heart.
Yeah, it's off this topic, but my senior year in college, I was deciding whether to go into mathematics or statistics or maybe law. And I took a graduate number theory course in the math as a senior undergraduate, and it convinced me that I should probably not go into math. I'm happy with the choices that I made.
I fully sympathize with you.
Okay. The next person is Bill Heary. Would you please unmute yourself?
Question, then a couple of comments on the other questions. Thinking of the Goldbach conjecture or the Riemann hypothesis, or any of those problems that you cited, there seemed to be a way to prove. It sounds like the following. I think of something like the Goldbach conjecture, something where you either find a proof that it's true, or you just do an exhaustive search, which can never be really exhaustive, and try to find a counterexample. But because you can never go through all the answers, you'll never be able to use that as a way of saying it's definitely true. These results with the Busy Beaver function seem to be saying that if you can do that, attempt at an exhaustive search up until some huge number, that's enough. You don't have to go further. Am I interpreting that properly?
You've got it exactly right, Bill.
Okay, that's kind of mind-boggling.
That's why I found this topic very interesting, and I thought maybe some people in the math interest group would find it interesting for that reason.
That's very interesting. I'm surprised that I hadn't heard of that kind of result before, because I've been reading various things related to number theory and unsolved problems, and I hadn't come across that as a way of saying, hey, there's a finite point we can stop. Pretty
Yes.
far out there, but okay. With regard to, somebody made a comment about Gödel numbers being integer at one point and then saying something about transcendentals. Gödel numbers are integers. They're not prime. They are the representation you typically get of a unique representation as a product of primes to powers. So, and they can't be transcendental because transcendental are real numbers. They're not even rational, so that wouldn't count. You also were talking about the idea of a statement that is true, but you can't prove it in the Gödel sense. And you were saying you could add that to the axiom system. If it is a Gödel statement, then you cannot prove it's true or it's false. So if you can prove it's false, you might logically say, well, that makes it true. And you can add it into the axiom system and have an expanded mathematical structure. But on the other hand, you can't prove it's false either. So you could also add the negation of it instead of the statement that you think is true, because that is equally not provable, either true or false. So either the statement or its negation can be added to the axiom system and it'll still be consistent.
Yes, these are very intriguing aspects of what can we do in mathematics and what can we not do in mathematics. And not everything in the world is true or false.
Right.
As we all know, there are paradoxes, statements that can't be proven either true or false.
But the other interesting thing is you can start with other axiom systems that might seem they're different statements, but that might be more intuitively correct. And you might be able to get ways to prove some of these things with a different axiom system you start with. And there's been some work looking at trying to look at some of these Gödel statements and with a different axiom system, because it's all based on the axioms. And we start with some basic axioms, particularly the piano axioms, and work from there. If you had a different set of axioms to start with that still gave you all the things you want in arithmetic, conceivably you could start proving some of these Gödel statements.
I think that's an intriguing thought. When I look at what you can prove with complex numbers and complex analysis, there are many more things that you can prove much more easily than you can more directly without complex numbers. So finding the right axiom system, if you like, is a very good thing to do. And I also have noted that when you think about a problem, finding the right abstraction with which to formulate the problem can aid significantly in finding solutions to the problem. So finding the abstractions with which we should represent problems is a creative task, but I don't see how we can completely automate that, even in spite of what the people who are engaging in AI do today.
Definitely agree with that. It's AI is basically statistics, which means it's not necessarily going to be true. It's not provable.
Oh,
You might be able to get very close with examples, but it's still not provable, as far as I know. At least there's machine learning techniques that are being talked about and used very heavily now. It's just advanced statistics.
yeah.
Okay. Do you have any further questions, Bill, or?
Oh, yeah. Another question about the Goldbach conjecture and the Riemann problem. They picked states, 27 states for the Goldbach conjecture and 744 for the Riemann. But how did they come up with those numbers?
Both of them are tour de forces of reasoning. And if you're interested, I strongly recommend reading the paper by Scott Aronson on the Busy Beaver frontier, because when he describes what he did to reduce the number of states of his Turing machine from, it was in the thousands of states initially, because a Turing machine is just a computer program. So the first computer program that he did on a Turing machine to enumerate the solutions to the Riemann hypothesis was enormously big. And so he used a lot of compiler technology and arguments similar to Collatz type mappings to reduce the enormous number of states he had from his first Turing machine to a modest 744. And if you look at the Shenlin's PhD thesis, just proving that Busy Beaver of 3 has the value of, I think it was 21. He had to resort to all sorts of ingenious arguments to say that there was no 3-state Turing machine that could make more moves than the champion one. So the fact that there's no systematic way of computing the Busy Beaver number forces you to reduce to ad hoc methods to try to find particular cases that you could solve. So when I took a look at the Busy Beaver webpage that's on the internet, this is a game that's being played by people who have a lot of spare time on their hands, trying to even just come up with these crude lower bounds, bounds on the size of the given Busy Beaver function. So it's a recreation, and I guess this is what Radó suggested, that finding Busy Beaver champions should be a game, not a mathematical pursuit. Maybe it's like what Walt mentioned, that working on the Collatz problem, a lot of mathematicians say, don't waste your time on Collatz mappings because they just suck you in and it's a waste of time.
And do they use the same analysis to determine whether the Busy Beaver does come to a halt independent of the value of n?
You have to show it for all possible Busy
Like
Beaver machines of size n. So
and so if n increases in number, we always know that the machine will halt.
no, you have to write the program, the Busy Beaver program, so that it's guaranteed to halt. It's very easy to write a Busy Beaver program that doesn't halt. Like if you have one state, you can just change a 0 to a 1, move right, and repeat. And that's a one-state Busy Beaver machine that's not a champion, and it never halts.
Is there a Busy Beaver problem that could halt, but you'll never know it?
Oh, this is exactly what Scott Aronson points out with one of his observations, that there's a given value of n for the number of states, such that if you want to prove the statement that a Busy Beaver machine with n states, where n is greater than that magical number, has a value equal to k, that's not provable in Zermelo-Frankel set theory.
All right, thank you.
Okay. Do we have any further questions? Well, I thank Al for giving such a fine talk on a topic that really pushes everything to the boundary of theoretical computer science and mathematics. And I hereby conclude the Math Interest Group meeting. Thank you very much.
Goodbye, everyone.